Okay, so let's go ahead and we need to get, why are you being so slow today? Okay, algorithms, slides. So we left off on numbers in here, and was going through the slides last time to make sure that I have this. Now, we introduced the Euclidean algorithm for the greatest common divisor. And what we're going to go over today is the extended Euclidean algorithm, because that is extremely useful for what we're going to need to do, we've talked about how to do addition in modular arithmetic, division in subtraction, multiplication, but division in modular arithmetic we said was a hard thing. So what we're going to do, so as an aside to work up to that, we're reviewing how the greatest common denominator, greatest common divisor works. Okay. So we have this basic Euclidean algorithm that swapped things. That had, if we have the greatest common denominator of A and B, where A is bigger than B. If we hit 0, we're done. Otherwise, return B A mod B. In other words, return the smaller number and then the bigger number modded by the smaller number. Essentially, what we're doing is we're doing a lot of subtractions all at once with the second step to try to find the greatest common divisor. And what we had over here was a lemma that I didn't get to, which was saying that if A is greater than B and 0, then this other number, this number right here, A mod B, is less than, it will be less than A divided by 2. Why is this useful? Because that means we'd be getting more than every step would basically be halving the number at least. Every step of this halves A, essentially, A mod B, right? We generate a number that's half of A mod B, which makes the numbers go down very fast. So so the way this proof works is that we have two possible conditions. We have, what if B is less than A divided by 2? Okay? Well, in that case, we know that, if B is less than A divided by 2, right, then we can conclude that A mod B has got to be less than that, because A mod B, by definition, has to be less than B. Because remember, the possible range for A mod B is 0 up to B minus 1, right? That's the only possible range of numbers that that A mod B can be. And that's small, and B minus 1 is smaller than B last I checked, so there we go. So it's got to be, so if we're starting with B less than half, great. And on the other hand, if B is greater than that, then A mod B is equal to A minus B, right? And that would be less than A divided by 2. What does that mean? Basically, we'd just be removing only one, rather than doing multiple subtractions by doing modulus, we'd be doing only one. But we're going to take off more than half because B is bigger than A over 2. We can see that graphically, that if A, and so we've got a nice graphic over here where basically we show that if A mod B, so our first case is on the left. If B is less than A over 2, then A mod B is going to be this remaining segment. Okay, it's going to be less than that. If, on the other hand, B is greater than A mod 2, then A mod B is going to be this remaining segment. Make sense? No? Anyway, point being is that we are going to is that this algorithm works fast, which is good because each call because we're still dealing with bits as our input size. So since it's logarithmic, we're taking off at least 1 bit each step, right? Which now 1 bit each step sounds not so great. And so each of those involves a quadratic time division. It says, then we're going to be doing n cubed. So this is, it's good, but I mean, like, it could be better. But again, for big numbers, it can't actually be better. But this is what's weird about algorithms. So when opposed to coming from data structures, when you come from data structures, this is not a great runtime. And when we're talking about this, I mean, n cubed. Okay, that's fine. So what in the world is the extended Euclidean algorithm? So there is this property that numbers have and it's called and these are Benzoics numbers, I believe, which is not in your textbook, but this is what it's expressing. The idea here behind this is that if you've got some GCD, and I'm rewriting essentially what we've got down here, but if you've got some GCD that's A and B, okay? If you've got some greatest common denominator of A and B, first off, that's going to be D, no matter what. It divides both of them, okay? And we know it divides both of them. Now, this D, this greatest common denominator, can be expressed in the form of AX plus BY, okay? Where, again, A and B are the numbers we're finding the greatest common denominator of, and we can say we can express this in the form of AX and BY. What's important to note is that these two numbers, X and Y, are not unique. You can have multiple solutions for them. So for instance, let's go ahead and do a trivial example. Without one that's so trivial we won't really have to run an algorithm for it. GCD of 3 and 2. What's the greatest common denominator of those? It is 1, right? Okay, it's greatest common denominator, and we can express this in the form of 3. So we can reform that 3 times 1 plus, and now B is 2 times negative 1. Okay, so so X and Y don't have to be positive. But to show you that they're not unique, we can pretty much do, let's see, 3 times 3 plus 2 times negative 4, 9 plus negative 8. So again, these things are not unique. You can generate X and Y with these. Now, the extended Euclidean algorithm generates both these numbers. Okay? The extended Euclidean algorithm generates both these numbers, and it looks like this. You'll see online that there's a lot of different solutions about how to, and in your book it goes into, okay, we should work on these things and strike them out to do we should work. Okay, it doesn't go into it, but if you check your textbook, okay, and for future reference, if you check it on page 22, you'll see that they have these examples of how to strike it out. Also over here, you're going to see, if you look on YouTube for examples, you'll see we should underline and keep things common factors. I watched all those videos. None of them made sense to me, to be honest. They just didn't, this seemed a heck of a lot simpler, which makes sense because I'm a computer scientist, and I mean, it was fairly straightforward to, okay, I'm going to close that window. I mean, the breeze feels nice, but my papers are going everywhere. Yeah. Woo. Okay, so what it says is basically we are going to return 2 positive input, 2 positive integers, two positive integers a and b, and we're going to find the greatest common denominator of them. We're going to return x, y, and d, where d is the greatest common denominator, the thing we probably care about. But we're also going to return x and y, just for the heck of it. Why? We'll see in a bit. But okay, how does this work? It says we are going to do x and y. So we're going to do, so if b is equal to 0, we return 1, 0, a. Then we get back x, y, and d from a recursive call. And then we return y, x minus a divided by b, get the floor of that, so do integer division in other words, y and d. So let's go ahead and run through that. And conveniently, we have one of those in front of us, in front of you for your quiz, but that's not the one we're going to go through. We'll work on that. I'll run through it once myself, and then I'll give you a chance to try it yourself, and then we'll go over the answer together. Sound good? Again, this quiz is not really so much a quiz as something as basically showing you what kind of questions to expect from a quiz. Okay? So, and also because I wanted to get something, on the board, considering the current time in the semester, which is technically would be week 3 in a normal semester. So, okay. So the way I do this, rather than like doing the weird crossing out algorithms, is I like to write down a, b, and then x, and then y, and then d. In other words, I write down the inputs and the outputs. All right. So I'm going to use 25. Find the greatest common denominator of 25, or divisor of 25 and 11. We know that that's going to be 1, just because they're both, just because 11 is a prime number and a is not a multiple of that prime number. Okay. So how does this work? Well, we can't figure out what these are yet because we have to do a recursive call. So let's look at this. If b is equal to 0, return, well, it's not equal to 0. So now we need to do extended Euclidean algorithm, which says let's do b. For the next step, it's going to be b. Our b is going to be in the a column, right? That's what's going on over here, right? And then a mod b. So 25 mod 11. What is 25 mod 11? 25 minus 22, which gives us 3, right? Make sense? So now we're going to consider as though our inputs were 11 and 3, finding the greatest common divisor of 11 and 3. Okay? Again, we skip down here and we go down to extended Euclidean algorithm of b. 11 mod 3. What is 11 mod 3? That would be not 11 minus 9, which gives us 2, right? Okay, now we do this again, which is 3 mod, which is going to be 2 and 3 mod 2 will be 1, and then this last column will be 1 and 0. So now that we're at this last column, though, we can actually get cracking at this, because we see b is equal to 0, so we return 1, 0, and a, which is 1. Okay, so also note that basically that we have what we're returning, y over here over here. These first two returns don't have anything in them related to d. The only thing that we pass back, and d is just always passed back over here. So d is going to be the same no matter what. Make sense? So so I'm just going to go ahead and fill that out so I don't worry about it later. So now we just worry about x and y. So 2 got back 1 and 0 as the x and y. So what we're going to be doing is that we're going to fill in our x and y using the y and x from below. Okay, so 0 from here, because that's what the y below is, and x prime, and so x minus a over b. So first off, x is 1 minus a over b. Well, a over b, that's 2, but we don't have to worry about that because that's going to be multiplied by y, which is 0, so it's going to be 1. This often happens where we flip that. So now we go up to here, 3 and 2. So x is going to be the y, and then y is going to be x, which is 0, minus 3 over 2, which is 1, times y, which is 1. So 1 and 1, right? So I said 1 times 1. Oh, actually, negative 1, right? Right? Negative 1. Yep. Because 0 minus 1 times 1. Okay. Now over here, 11. So now over here we have negative 1 and 1 minus 11 divided by 3. 3 so let's see actually. So it is 1, well technically it is 1 minus 3 times negative 1, right? Which would be positive 3, which turns this entire thing into 4. Okay? And then finally over here, going to double check my math. I did do this a couple of times. Or not a couple of times. I've done this like particular algorithm a few times. So like I tried all the side ways of doing it, and honestly, they did not work nearly as well. Yep, okay. I'm doing it right. Okay, now the last one, 25 and 11. 25, so for x, it's going to be 4, and this is going to be negative 1 minus 25 over 11, which is going to be 2. So negative 1 minus 2 times, so that is going to be negative 9. And you can check the equation. And so we can check this equation that, so this is what we return. We return 4, 9, and 1, and we can check this equation. 25 times 4 plus, sorry, this should have been negative 9, plus 4, sorry, not 11, not 4, times 11 plus times negative 9 is equal to, well, that's 100 plus negative 99, which is going to be 1. So we get our answer. Everybody kind of see how that works? All right, so the example that I gave you on your sheets is much simpler. So go ahead and give it and take a shot at it. And you'll know, and again, it kind of has its own built-in self-checking mechanism, right? It's got, which is that you can take your answers and feed it to the equation. And also, it's fairly easy to calculate what the greatest common divisor is for your thing just off the top of your head. I'm going to try to lower the temperature in here. Remember, first thing you want to do is set up A, B, X, Y, D at across the top.
no space.
Yep, okay. All right.
I don't understand that.
Let's see, it should be the floor function. So you take the floor, so in other words, it's integer division, 25 divided by, integer 25 divided.
Should be two.
Yep, exactly, should be 2. Or at least 25 divided by 10 should
Okay,
be 2.
yeah, now it makes sense, yeah, now the answer is.
So you should have got in, so let's see, are you at the end yet? Let's see where you're having this. Okay.
I was writing 12.
Uh-huh.
I was doing 25 divided by 2.
Yeah, okay. Yeah, so the answer you should have gotten was x is 1, y is -2, and d is 5. Which again is fairly easy to check. 25 minus 10 times 2 is 5, right? That's what I like about this one. It's fairly easy to check. It's also not so bad to code up. I'll go ahead and code it up now because this is a tool we will need soon, okay? And yes, I'm actually going to code in this class, Wonders of Wonders. I'm going to do it in Python because Python is quick and easy, and I'll go ahead and do this. So we're going to need this for, for doing RSA. Extended Euler, which will return, so wonderful thing about Python, so it's going to take in A and B, and Python is going to, if you're not familiar with it, it's going to look so much like pseudocode, it's crazy. That's the weird thing about Python. Okay, so A and B, you need to move out of the way. Okay. So Euler, A and B, we need to do, sorry, let me go ahead and get the, I'm going to pull up my page so I can see it again, which is, we take an A and B, okay? So first off, we're going to do so I'm going to do so we want A to be greater than B. If B is greater than A, okay? Then we need to do something about that, just simply because that's what we do when we're coding. So if b equals 0, we are supposed to return 1, 0, and a. And yes, you can return multiple things in Python. That's a lie. You can only return one thing in Python. What it does is that it groups it together into a group of multiple things called a tuple, which is a lot like a list. And it just pretends that it's multiple things. But you can unpack it and basically gives you a lot of flexibility. You can so yes, you can return multiple things in Python, but it's technically going to feel like not. And look, like this, I am basically coding the exact same. Oh, it's not Euler, it's Euclid. Why did I put Euler? Because because I'm on autopilot, and we're going to be talking about Euler in a second. Okay, x, y, and d is going to be A is going to be B, A mod B. Just like that, right? Okay, and then return y x minus A divided by B, right? That's integer division right there. Okay, let me turn down the volume. Integer division right there times, and let's go ahead and make sure that order of operations is respected, times y. Return D. Okay, and I went ahead and coded this up earlier, but I like live coding in class. So give me a second to, so give me a second to pull up basically what I had as a test case. Because because honestly, I don't want to waste the time with the formatting, with making you sit through my formatting. And we can see that basically that it solves for 50 and 15. It figures out the greatest common divisor is 5, and it says 50 times 1 plus 15 times negative 3 gives us 5.
So, can you explain the pass in Python?
The what?
Pass.
Oh, past. Yes, that means I'll get back to it later. So what we needed then later is now. So basically, it's because the way Python works on needing indentation to work with everything, it's expecting code in this if statement, but I wanted to come back to it later. So this is if B is greater than A. In that case, we need to return, let's see, the extended Euclidean algorithm for, so it's going to return, but if we do just this, okay, it's not going to be correct. I'll show you what I mean. We do 15 and 50. It's not going to be correct. It's going to give me 15 times 1 plus 50 times negative 3 is 5. It's not going to give me the correct, it's not going to give me the numbers in the correct order. That's what's going on over there. So what we're going to do is instead say, is get return, is that we're going to get y, we're going to get x comma y comma d out of this. Return y, let's see, how do I don't want to bother, yeah, I get y xd out of this. xd out of this, and I want to return x comma y comma d. So I just need to make sure that since the inputs are flipped, I flip the outputs. That's all that was for, because I you know, I don't want to write anything to enforce the rules there. Okay, so that's our extended Euclidean algorithm. We'll come back to it because we're going to need it. Specifically, we're going to need it for, finally, this part, the modular inverse. So the modular inverse is this funky little property. We typically write on the modular, so if A, let's go ahead. So if A, the modular inverse of A, we typically denote that as A negative 1. That's how we do the modular inverse here. And what that's saying is A times A, A times its inverse is going to be 1 mod n, okay? So in other words, the inverse is the thing you multiply against to get 1, okay? There's only, you know, and what that number is exists in a module in that space. The inverse doesn't always exist, by the way. Like, for instance, there is no inverse for 2 in mod 6. There's no inverse. There's nothing that will satisfy this equation. It's saying down here. There's nothing that's going to satisfy this equation, which is there's no x that will give us that, right? We can check it ourselves. 2 times 1 gives us 2. 2 times 2 gives us 4. 2 times 3 gives us 6. 2 times 4 gives us 8, which is 2 again. So we're always going to get an even result, which is not going to be. It's not. So there's no. So first off, the integer does need to be an integer here, and again, it's just not going to exist for everything. In fact, it only exists. The modular. So the modular inverse only exists if the GCD So the modular inverse of some number A only exists if GCD A of n is equal to 1. That's the only way a modular inverse can exist. This is saying basically, so another way to phrase this that we're going to be using a lot in the upcoming minutes is that A and N are coprime, meaning that they don't have a common divisor. Okay? They don't have a common divisor. They can only be divided by 1. They're both only multiples of 1 with regard to each other. That's what it means to be coprime. Okay? It also, so now also, how do we find this? Well, it just so happens that we know that this equation that we've got an equation here. Ax plus nd, sorry, nd. Where did I get the d from? Ay. We've got an equation here. Okay? And so, what we can find is that Ax is going to be 1 mod n. You can work it out itself, but basically if we run that greatest Euclid, if we do that extended Euclidean algorithm, x is going to be the, if we run the algorithm on this, a and n, then x is going to be the inverse. Now, why is that? Let's see. Because, well, we get it from the equations. Ax is equal to n plus my, so if we go ahead and take a and x, that's going to be equal to 1 minus ny, and then if we mod to make congruent n, and so if we mod this by n, okay, then this goes away because it's a multiple of n, right? Becomes equal to 0. So that's how we get there. So we say a of x is congruent to 1 mod n, so x has to be the, so in other words, this entire thing, this Euclidean algorithm not only gets us the greatest common divisor, it also gets the modular inverse of A in respect to B. So useful algorithm. That's why we care about it. We got all this extra data at for another cost. Now, a brief aside here. I mentioned that basically that we had, and again, this is not something that appears in your book, but it's useful to know for Fermat's-Lell theorem. Sorry. I find this interesting. This is all stuff I learned at the PhD level that's kind of fun. So two numbers are coprime, right? If they don't share a common divisor. There's something called Euler's totient function, which is represented by the Greek letter phi. And that is the number of numbers it's coprime with. In other words, the number of other numbers that are other natural numbers that are that doesn't share a common divisor. For prime numbers, if n is a prime number like 7, so for instance, if this is 7, then that number is going to be 6 because it's coprime with 1, coprime with 2, coprime with 3, coprime with 4, coprime with 5, coprime with 6. There's no common divisors there. Make sense? Now, for a number like 6, okay, let's go ahead and figure that out. 1, 2, 3, 4, 5, 6. 6 shares a common divisor with itself. We leave 1. 6 is divisible by 2, right? So they share a common divisor of 2. It's divisible by 3. They share a common divisor of 3. And 2 and there's a greatest, and 4 is not co-prime with 6 because they have a greatest common divisor, 2, right? 6 is co-prime with 5 because 5 is a prime number over here, so 6 divided by 5, well, 6 divided by 5 and 5 divided by 6 doesn't work out, so its quotient is 2. Why am I talking about this? Because it's useful for later. So anyway, why did I talk about this co-prime, this modular inverse kind of thing? Why do we care about a dx is 1 mod n? Because this is the only way we can do division. The only way we can really do division here is multiplication. If you want to divide by, if you want to calculate A divided by B, okay, if you want to calculate A divided by B, there's only one way to do that in mod n, which is we need to calculate A times B's inverse. Make sense? And how do we get B's inverse? We have to run the Euclidean algorithm. So, okay. And again, that leaves, because we're doing the Euclidean algorithm, it's going to be n cubed time, where the n is number bits. All right. So now that we've got all of our modular arithmetic and all of our modular operations to the side, okay, first off, expect on Thursday's quiz for one of the questions to be to compute the inverse of a number, which is just a fancy way of me saying run the Euclidean algorithm, which we just did twice. Okay, so that's going to be one of the questions on a real quiz on Thursday. And again, these quizzes I only expect them to run a few minutes. So there's 2 problems that are kind of sort of related. One's hard and one's easy. Factoring is hard. In other words, figuring out for some number what its factors are. For instance, figuring out that the factors of 100 are 5, 5, 2, and 2, right? I only know that because I built that in advance. For 100 is 25 times 4, which can be further factored, right? That's unfortunately a hard problem for computers. Okay? And really the only real way, so we can't really tell if a number is prime other than so one of the ways you can test if a number is prime is by trying to factor it, basically going up to all the numbers below square root of n. Why square root of n? Because n, the square root of n times the square root of n is the number you're looking for. So we test all the numbers below that, and we see can it be divided by any number that's less than the square root of the number you're looking for. So in other words, we can test 100 by testing all the numbers from 1 through 9 on it. And if it's divisible by any of those, then we know it's a prime. Then we know it's not a prime number. Okay. There's other ways called like the sieve of Aristophanes to figure out your primes and stuff like that. But I mean, unfortunately, doing it that way is factoring, and factoring is hard. Instead, we're going to use a couple of cheats to get there. We're going to be using a randomized We're going to be using an algorithm that should be doing it, and we're going to be exploiting something called Fermat's little theorem. So Fermat's has a couple theorems that sound very similar. Fermat's little theorem, which has been well known for a long time, and then we have got something called Fermat's last theorem, which only got solved in the 90s. The 1990s. So anyway, what it says is that if f is prime, so this is actually pretty remarkable. If p is a prime number, if we've got some prime number, then for every number less than that, from 1 to p, every single number, a to the p minus 1 is congruent with 1 mod p. In other words, every number, well, we'll see how that helps us. But remember that we kind of saw something that like this. That means that every number is coprime with it, obviously, but that means every number has an inverse with it. So anyway, note that basically that we'll note that this is not inverted, right? This isn't the other way around, but we're going to play with it as though it is, right? This is a if then, not a if and only if, right? So if a to the p minus 1 is congruent with 1 mod p, then p is prime is a false statement, is not necessarily a true statement. Okay, keep that in mind, but we're going to use it like it is. Okay, so how do we prove this? I actually really think this proof is silly, and it's clever, but let's go ahead and prove this. So let's go ahead and set. We're going to set two numbers. We're going to set a is equal to 3. It works for any number, and p is equal to 7. Okay. So, and notice that basically that we've got all this. We've got all the numbers that exist in that modulo space, which is 1, 2, 3, 4, 5, 6, and multiplying each one of these numbers by 3 does a very interesting thing. 1 goes to 3, 3 goes to 2, 2 goes to 6, 6 goes to 4, 4 goes to 5, and 5 goes to 1. And 1 goes to 3, and 3 goes to 2. Basically, it gives us a loop. That's what it's showing us. This gets a loop. Which is, so it's saying that basically if we keep if we multiply 1 by 3, we get, in mod 7, we get 3. Multiplying 3 by 3 in mod 7 gives us 9, which is 2 in mod 7. 9 mod 7 is 2. 2 times 3 in mod 7 is 6. 6 times 3 gives us 18 mod 7, which is 4. 4 times 3 gives us 12 mod 7, 15, yeah. So 14 minus 7, sorry, not 14. 14 times 3 gives us 12. 12 mod 7 is 5. 5 times 3 gives us 15. 14 and 15 are differ by 1, and we're back at the beginning. So, in other words, we can rewrite each of the numbers, 1, 2, 3, 4, 5, 6, as 3 times mod 1, 7, 3 times 2 mod 7, 3 times 3 mod 7. They're going to be equal to each other. That's the same set. They're not appearing in the same order, by the way, obviously, because 3 is over here, and then 6 is over here, but it's the same set. That's what we care about. Make sense? So let's go ahead and demolish this set by multiplying everything, by taking everything and multiplying the entire thing, every element in it. So we're going to multiply everything here together, just because. Just humor me. We're going to multiply everything in this set together. 1 times 2 times 3 times 4 times 5 times 6. We know that. That's 6 factorial. We're not going to calculate it because that's annoying and not useful. And then because we're dealing with modulus, we're going to write congruence rather than equal to. So 3 times 1 mod 7 times 3 times 2 mod 7 times 3 times 3 mod 7 times 3 times 4 mod 7. So we've got 1, 2, 3, 4, 5, 6. We've got 6 factorial, and we've got mod 7 over here, and then we've got 3, we've got 6 3's multiplied together. 3 to the 6th, mod 7. These cancel. And we can do that division because we know that since 7 is prime, anything we have is coprime, and thus we'll have an inverse. So we know that we can cancel there. We couldn't cancel if we couldn't divide. But because we have a modular inverse, we do. So that becomes 1 is equivalent to 3 to the 6th mod 7, or better yet, 3 to the 6th mod 7, okay, or 3 to 6 is congruent to 1 mod 7. Okay? So that shows it for one example, and then we can just take the same exact thing over here, where we have 1 all the way to the p, and then we have, so we have 1 to p, and then we select some a times 1 mod, mop. Got a bit excited there. A times 1 mod p, a times 2 mod p, et cetera, okay? And we do the same thing over here. We multiply, we just do that. We just take the entire set and multiply it against every element in there. That would be p factorial over here. And on the again, on the other side, we get p factorial times a to the p minus 1, because there's p minus 1 elements, and we multiplied every element in there by a. And again, the same logic and mod p. And the same logic holds. We just can simply cancel out the p factorials, and we get mod is, and we get what we're looking for. So it's been proven. There's other ways to do it. Cool geometrical proofs. This thing has been proven, is like it's one of those proofs that basically you can take a proof, like a nice proof, and like whatever, you can take you have a bunch of different ways to prove it. It's pretty nice. We're just proving various things. So as a side note, this is actually a generalized. This is actually a more specific version of a more general theorem called Euler's theorem, which is as follows: a to the, so same thing, which is going to look very similar. A to the, this is a more specific version of this, which is Euler's theorem. There's that totient function again. That's Euler's theorem, by the way. Some a to the raised to it to the is, so some a raised to the totient of n is congruent to 1 mod n. Now, if n is a prime number, right? If it's p, how many numbers are co-prime with a prime number? P minus 1. So this allows us to do, so that's just so Euler had a much more general version of that, which is pretty cool. So again, this kind of indicates that the totient function is going to be it might show up again at some point. Now, Fermat's little theorem is super useful over here, as you'll see in problem 3 on your quiz. In problem 3 on your quiz, see if you can apply that to help you out to solve that. Okay? And it looks like some of you already have to figure that out. So, yeah, you simply use the fact that so for problem 3 on your quiz, right, you've got 4 to the 37th power and mod 13. Note that the modulo space is a prime number, right? So now use that to write. So now apply Euler's theorem, the Fermat little theorem to that, right? 13, which means that we can put any a we want in there. 4 would probably be useful, right? So we know that 4 to the what is congruent to 1 mod 13. 4 to the 12th is congruent to 1 mod 13. Does that make sense? So, and then I happened somehow to choose 37. So 12, so you can probably figure it out from there. We'll take a break in a bit right before we do RSA. We've got almost all the components So, yeah, it should be, so 4 to the 12th
Mhm.
is congruent to 1.
Mhm.
So that also means that 4 to the 24th is congruent,
Mhm.
and 4 to the 36th,
Oh, okay.
Right, you see-
Okay.
right? So so with problems like 2 and 3, the first thing you should check is the modular space a prime number? If it is, you can simplify what you're doing with Fermat's, using Fermat's last theorem as an export. Right, so, yeah, that should be 4. Yeah, because, no, you have, no, the 4.
Oh, yeah, one more time, wow, I was adding it.
Yeah.
Yeah, 4.
Yep, so Fermat's last theorem really can help speed up that kind of problems like 2 and 3. So first thing you want to do, like if I give you a problem, you're going to get a problem like this on the quiz. So the first thing you should do is check, okay, is the space I'm operating in a modular space? You know, is this number a prime number? And I'll use something that, and I'm not going to make it a very hard prime number because again, I want you to try to be able to kind of do these without calculators. Also for the quiz, feel free to bring in notes. You know, sorry, for quiz, by notes I mean like, feel free to bring in a front and back sheet. You know. And if you want to collaborate on generating that note, you can. I'll tell you what I want you to study, okay? So Fermat's last theorem, 1, the extended Euclidean algorithm, another.
Are you gonna take this sheet?
What? No, you can keep this. You can keep this. Now, what about for problem 2? You just kind of have to do that one the old-fashioned way, which is compute 3 to what power did I choose?
50.
3 to the 50 mod 10. Mod 10's not too bad because the math on that is really, the math on mod 10 I like to do because it's nice and easy. It's just the last digit of something. So, all right, take a moment to try to solve problem 2. Let's see. Let me see what you did over here. You got your answer over there? Okay, yeah, that's correct. Yeah, this is essentially similar to what I did over here, which is, right? Which is I did that, and then I did that. Yeah, you see how it is. All right, looks like you both are having a bit of trouble, are stuck a little bit on it.
Yeah.
Okay, so let's go ahead and, so when you're in a situation like this, first off, I'm giving you numbers like this because I don't want it to be, because I want you to be able to solve it like by hand. So, when you're, and again, this is what, again, normally I would give you quizzes in advance, but I want you to see what kind of questions I would give on a quiz. That's the entire point of this one. Okay, so 3 to the 50th mod 10, right? And the idea here is that we can do substitution whenever we want. So if I can figure out the answer to a exponent that's smaller than it, like 3 to the 3rd or something like that, then I can substitute it however I want, whenever I want. So let's go ahead and say, so we know that 3 to the first power mod 10, that's an uninteresting answer. That's congruent to, that's going to be 3 is congruent to 3 first mod 10. What about 3 squared? That is congruent to 9 mod 10. All right, now what about 3 to the 4th? Okay, because I might as well start doubling the exponent and squaring my answer each time. Because I don't need to calculate 3 to the 4th, I just need to take this number and square it. Which means now that is 81, which is congruent to 1 mod 10. So we now know that 3 to the 4th is mod 10. And now we're getting somewhere because we have something that is effectively 1. And 1 is easy to work with. So our original number was 3 to the 50th, right? Yes? So, so let's go ahead. 3 to the 50th, we can break that 50 how? Well, we've got 4. Basically, we need to basically break it into something that's a multiple of 4, and then plus and then times whatever's left over, right? Make sense?
Yeah.
Because then if this is a multiple of 4, then we can do this. So and it turns out you can break this into, if you do some quick math, right? You know that you could do 3 to the 40 times 3 to the 10th, and then you could subtract 4 from here to get another 3 to the 4 and another 3 to the 4, right? Like that. And then we can just simply take these, make this 3 to the 48th. 3 to the 48th, we just rewrite that as 1. Because again, wonders of modular arithmetic is that we can replace anything with its result once we know the result. So in other words, this resolves to 3 to the 50th, let's go ahead and make it prettier, is congruent to 3 to the 48th times 3 squared, which is congruent to 1 times 3 to the 9th, 3 to the 9th. I was putting the answer in the exponent, 3 squared, which is congruent to 9 mod 10. Make sense?
Yeah.
So, all right. So we learned Fermat's last theorem. Why in the world should you care? Because we want to generate. Because for RSA we need to generate prime numbers really quickly, big prime numbers really quickly, and we really want a way to test if something's a prime number. Now, remember, I told you that. So we've kind of have an idea here, which is that we just pick some a. So we've got this formula that if n is a prime number, all right, I'll let you finish copying that down. If n is a prime number, then a to the n minus 1 is congruent to 1 mod n. So here it's saying even though we know it's not going to necessarily work in reverse, okay? Even though we know that our original was if p is prime, then Fermat's last theorem, our little theorems hold. We're going to treat it as though it's an if and only if, right? We're going to treat it as we can go both ways. So we're going to pick some a, test that number, and if this test holds, it's prime. If we take that number, if we take some a, raise it to the number we're testing, minus 1. If that is congruent with 1 mod the number we're testing, then it's prime. Probably. The issue is, of course, that, like I said, we're kind of working under a false pretense here. There's specifically a set of numbers called Carmichael numbers that pass this test. Right? Because again, it's an if and only, right? Because if it's prime, then this holds. It doesn't go the other way around, but we're pretending it goes the other way around, right? Make sense? And so the numbers that pass this test, by the way, this is the other way you can see Fermat's theorem, little theorem displayed, right? We've been doing b to the n minus 1 is congruent to 1, but if you multiply both sides by b, you get b to the nth power is congruent to b mod n. Either works. It's the same equation, just more. This is just relates better to our inverse, which is what we care about here. So Fermat's. So we've got the first. So we've got these numbers. Here are some the Carmichael numbers. You've got 561, 410, 41. So they're rare. They aren't. They're fairly rare, but they, they do show up occasionally. There's an infinite number of them because there's an infinite number of numbers, okay? But they're rare, even though there's an infinite number of them. Infinity is weird, okay? So And it turns out, so there's a fun thing here that we know, that if this doesn't hold, so if a to the n isn't congruent to 1, in other words, if it's going to fail this test, then it's going to fail this for at least half of the numbers. Half of the a is less than n. I'm not going to bother proving that, but what that means basically is that the idea here is that if we ignore, so let's ignore our Carmichael numbers for now. If n is prime, then we know that a to the n, then Fermat's last theorem. If it's not prime, then it's only going to hold for at most half of the, then this test will be true only for half of the values. Only for half of the values of a, where a is less than n. So in other words, for this basic test that we're doing, pick some a, toss it into here. If n is prime, it's going to give us a correct answer. But if it's not prime, it's going to give us a false positive like half the time, at worst case. So how do we solve this? Do it a lot of times. A lot of times. So pick some k number. And now your chances of getting that wrong are 1/2 are now 1/2 to the kth power. Long story short, this is what we call a randomized algorithm. This is where some amount of error is tolerable. And because the error here, they're wrong with a very, very small probability. Think about it. If you test 30 numbers, so if we test 30 numbers to check if it's prime, check 30 different a's during this test, that's going to be 1 to the 2 to the 30th power. That's ridiculously small. That's close to like 1 billion. Okay? So that's good. Now on the flip side of things, how do we generate a prime number? Fun thing, if you generate an n-bit number, it's got a 1 in n chance. It's got a roughly 1 in n chance of being prime. Technically, it's that number, 1.44 divided by n, so a bit better than 1 in n. So if you just generate a random number, okay? So if we want to generate an n-bit prime number, we want to generate like a 50-bit prime number, then we just pick a random number, just, generate random bits of ones and zeros, test it, and if not, keep doing it. And it's not going to take too long. On average, it's going to take, on average, the number of bits you want amount of time. It's going to take a linear time linear to the number of bits. Okay, so now we can generate prime numbers. We can test if numbers are prime. We can generate modular inverses. So we're going to take a break here.
So that doesn't feel right if we generate a 2-bit number, it's always a prime.
Sorry?
If we generate a 2-bit number, it's always a prime number.
Generate a 2-bit prime number. Oh, 3, 1, 2, and 3. Yeah, that's true.
Then,
1 is technically not prime.
Yeah, but that if we do the math, is 1.44 over 2, which is lower than
1.44 over 2.
Like
This is as n approaches a large number.
oh,
Okay, I wouldn't ignore it for the small. I would ignore it for the small cases. This hence the approximately equal. We're talking about for large numbers. Okay, and it doesn't go into this. This is just something that's asserted by it. So yeah, I'm going to go ahead and pause this.